Good morning, everybody. This is Bilal Aiken from C2000 Motor Control Group, Houston. Today I'm going to talk about motor control theory and types of machine in general, and I'm going to talk about C2000 applications. So, as you know, right now we are proposing two new devices. One of them is Piccolo and the other is Delfino. Delfino is targeting high-end applications. It's like super fast and has a very large flash memory size and a lot of peripherals. And the Piccolo is targeting low-end applications, but it's still powerful to implement any kind of motor control application. The good thing about the Piccolo is the price is like around $2, even less, depending on the volume. And the features are like it's 40 to 60 megahertz device, and it has on-chip converters and DACs in addition to the previous C2000 devices, and it has like on-chip dual oscillator. It's featuring high-resolution PWMs and high-resolution frequency properties. So this is very important for especially digital power supply applications, because those people are asking very high resolution at the output. So high resolution duty cycle and high resolution frequency becomes a very important feature for digital power supply applications. But on the other hand, for motor control application, high resolution and high resolution duty cycle and high resolution frequency is not very effective, because for motor control we are working with large amount of currents, and the frequency is quite low, like 10K switching frequency or like 20K switching frequency. On the other hand, when we are talking about digital power supplies, it's like more than 100K frequency mostly. So that's why high resolution feature becomes very important for DPS, digital power supply applications. And Piccolo has 12-bit ADC again, and it's quite fast. Like as I'm going to talk later, it can sense the current through shunt resistors on the three-phase inverters, which is a very important feature for motor control applications. And it has CLA, on-chip CLA, which is a control low accelerator. And what you can do, basically, you can develop a CLA code and run the control loop algorithms on CLA, and the rest of the operation can be handled by a 28 CPU. Okay. Now, if you go to our next slides, as you know, we started as a C2000 group. We started with motor control. And right today we are doing power supply, different digital power supply topologies. We are controlling them, and the power line communication, automotive, LED lighting, renewable systems, and many other different applications. Okay. Now I'm going to start talking about the motor control and machine theory. I'll talk about DC motors, AC motors, especially induction motor and PMSM and BLDC type of motors, and then I'm going to talk about a little bit about switch reluctance and steppers motors as well. In this slide, what you see is the very basic picture of a DC motor. Now, in DC motor, there are a few alternatives. You can create the field, stator field, using magnets, or you can create the field using the windings, as shown on the figure. So, the field vectors, the blue field vectors, are kept constant during the operation. That's very important, because we need to remember all these features while we talk about FOC because FOC vector control or field control is nothing but imitation of DC motor control. So we keep this theta field constant during the whole operation. And if you go to the next slide, this is the rotor circuit or armature circuit. So the current is going through the brushes and commutators. So the red vectors shows the current and direction of current. So as you see here, only the horizontal coils can conduct current, which are aligned to brushes. That's another feature of DC motor, and it's very important again because as I will explain later, this will help us to maximize the torque generation. So in actual DC motor, we have like several conductors like this, maybe tens, hundreds of conductors like this, and only the horizontal ones, which are aligned to brushes, conduct the current. Okay, here in this figure, we are observing how we generate the torque in DC motors. So the blue vector, blue field vector, is the vector I showed in the very first slide, and the red one is created by the armature circuit. If you remember from like high school physics, right-hand rule, the current flowing through the armature circuit will create the red vector, red B vector, field vector, and the interaction of these two vectors will create the torque. So if you look at the formula at the right hand side, the torque generation is B stator times B rotor times sine theta. In order to maximize the torque generation, we need to make sure that the theta is 90 degree, because sine 90 is is equal to unity 1, which is the maximum. So during the operation, if we can keep this angle 90 degree, we can maximize the torque, which means that the blue and red vectors should be orthogonal to each other. So in FOC, basically, again, we are going to imitate this philosophy. And here's another picture when the rotor starts spinning. As you see, as the conductor moves a little bit, okay, it's not aligned to brushes anymore, and there is no path for the current. So it doesn't, conduct current anymore. Only the horizontal ones can conduct the current. So when we go to previous slide, the horizontal one creates the red field vector, which interacts with the blue field vector. Okay. Since only the horizontal ones are excited, we guarantee that the red field vector is orthogonal to the blue field vector. So as the conductor starts spinning, it doesn't draw current anymore, and the next aligned conductor starts conducting current. Okay, here I summarized the basics of DC motor, which is important to understand the basics of field control. Previously, DC motors, the brush DC motors are used very commonly, but today most people are replacing them with BLDC type of motors or PMSM type of motors, because although it's easy to control the DC motors, brush DC motors, and it's cheap, the brushes cause some issues like electrical spark, EMI problems, audible noise, and you need to, of course, maintain the brushes and replace them periodically. And you cannot go to higher speeds, so that's why DC motors are becoming less and less popular nowadays. What we can do with DC motor, we can control torque, speed, direction, and position. And the control scheme is very simple, like on-off approach. If you want to control the speed and direction and position, we need to sense the speed and position using an encoder. And the topology is very simple. It's an H-bridge for bidirectional type of motor drives, DC motor drives. If you use like unidirectional drive, in that case, what we need to do is we need to use just single H-bridge. That's it. Okay. Now, in addition to DC motors, today I'm going to talk about the brushless motors. Okay, the previous motors were commonly mentioned as brushed DC motor, and these types of motors are called brushless motors because they don't use brush anymore. So, which means that we don't need to inject current, or we don't need to energize the rotor circuit. It's basically because the rotor has magnets on it, permanent magnets, and these magnets are creating the field. So we have a field source. That's why we don't need to energize the rotor circuit, and we don't need brushes anymore. So there are two types of PM motors, basically. I mean, I'm talking about the very popular ones, BLDC type of motor and PMSM type of motor. Okay. Now, here in this slide, the picture belongs to a BLDC type of motor. As you see, there are magnets on the rotor, rotating part, and phase windings around the stator. Now, the difference between BLDC and PMSM type of motors, first of all, they both use permanent magnets, and they are pretty much same, except the stator structure. As shown in this slide, the stator winding distribution, okay, is not distributed sinusoidally, but the phase coils are, located as a chunk of, coil turn. So that's why they are creating trapezoidal back EMF, which means that if you do not power the motor, okay, and observe the motor terminals using a scope and spin the rotor using your hand, you will see trapezoidal waveform, which we call back EMF. But on the other hand, the PMSM type of motors, the stator has like more slots, like 50 slots, 60 slots, 40 slots, depending on the structure. And the windings are very carefully distributed to create sinusoidal waveform in the air gap. So again, if you look at the motor terminals using a probe and spin the rotor using your hand, you will see sinusoidal waveforms, sinusoidal back EMF waveforms. So the difference between PMSM and BLDC type of motors are nothing but stator structure. The rotor is pretty much the same. And the good thing about these motors, again, we don't need brushes, so it's we don't observe audible noise or electrical noise or sparks or EMI. And PM motors, these brushless PM motors, they are synchronous motors, which means that when you energize the stator, we create a rotating field in the air gap. I'm going to talk about this later. And the rotating air gap is synchronized to rotor, which means that the rotor follows the rotating air gap, because the rotating field in the air gap behaves sort of like a electromagnet, and the rotor magnets follow the rotating field. So they are synchronized to each other. They are, very efficient, and they have very high power density. Because the magnets are creating the flux, we don't need to power extra circuit. Okay, so we don't waste additional power on these kind of motors, so that's why they are efficient and their power density is quite high. So when you compare like a PM motor with like same horsepower induction motor, you will see the difference. It's like mechanically 1/3 of the induction motor, sometimes 1/4, depending on the mechanical structure. So the operation is quite smooth, but the problem is when compared to the brushed motors, the control of PM motors are a little bit more complicated, especially the sinusoidal one. The algorithms running to control the PMSM motors are mathematically intensive. So we need powerful microcontrollers. On the other hand, controlling BLDC is relatively easier, and most cheap controllers can control the BLDC type of motors. But on the other hand, we hear lots of negative feedbacks about the BLDC operation, which I'm going to talk later in one of the next slides. So for high performance applications, people prefer PMSM type of motors with sinusoidal back EMF. Introducing the synchronous motor operation. See here, the horizontals are the field vectors, stator field vectors created by the stator, and the A, B, C phases are represented with the conductors, and the horizontal vectors are created by the phase A. And I'm going to talk about the three-phase operation as well. Here only one phase is excited. Anyway, and the horizontal field vectors are interacted with the magnet because they are sort of electromagnet right now. And the field of magnet and the field of stator are interacting, and that's how the motor spins. And the rotor follows the stator field, so that's why, very precisely, that's why we call these type of motors synchronous motor. They are synchronized to each other. So I'm going to talk later, but keep in mind this stator field vector is not constant. It's rotating counterclockwise. That's how the rotor magnets spin. Okay, now if you want to compare the BLDC and PMSM type of motors, first of all, BLDC type of motors, they have trapezoidal back EMF, and the PMSM type of motors has a sinusoidal back EMF. And the current, in terms of current, BLDC motors draw DC current, as shown on the slide. The black graph shows the current waveform, and the colorful one shows the back EMF waveforms. And the current is DC for a while, and then 0, and negative DC, and then 0. Okay, so the amplitude of the current is constant unless we don't change the load. On the other hand, the PMSM voltage and current waveforms are sinusoidal. Only two phases of the motor conduct current on BLDC motors, and the other third one is off all the time. I mean, like two of them are on at a time, at a single time, and the third one is off. And then we energize the other two, and then turn off another third one. That's how we spin the motor. And on PMSM type motors, all three phases are on at the same time. Because of the phase commutations on BLDC type of motors, we observe torque ripples, current ripples, voltage ripples, which cause sort of EMI problems, audible noise. That's the disadvantage of BLDC type of motors. For low-end applications, that's not very important, but for high-end applications, people prefer prefer PMSM type of motors in order to get rid of these disadvantages. And the maximum speed of BLDC is limited when compared to PMSM. PMSM is used for very high speed applications. When I say high speed, it's like 100,000 RPM. Otherwise, like below 20,000 RPM, BLDC can easily be used. And today, thanks to technology, I know that there are some BLDC motors spinning at 60,000 RPM. Okay, these brushless PM motors, both PMSM and BLDC, they are used to control torque, speed, direction, and position. In order to control the PM motors, we use traditional three-phase inverters, which means that 6 PWM switches are used. And we can apply like trapezoidal and sinusoidal approach. PMSM is PMSM is run using sinusoidal approach. BLDC can run either trapezoidal or sinusoidal. Since the motor is designed for trapezoidal application, the BLDC motors are mostly effective when we run them with trapezoidal control, not the sinusoidal control. But again, today we hear a lot of positive feedback about the sinusoidal control of BLDC motors as well, because we don't have like phase commutation when we apply sinusoidal control, and it's less noisy, less EMI, and less torque ripples. So I know some customers looking for sinusoidal control of BLDC type of motors. In the feedback, we can use like Hall effect sensor for both PMSM and BLDC type of motors. And since very precise position information is needed, people use incremental encoders or absolute encoders for PMSM type of motors. And the driver is three-phase inverter. And here we had a block diagram of the PMSM motor control. As you see, we have three-phase inverter, 6 switches, PWM1, PWM2, 3, 4, 5, 6. Now, PWM1 and 2 are phase A, controlling phase A, 3 and 4 controlling phase B, and 5 and 6 controlling phase C. Of course, when we apply the PWMs, we have to apply deadband in between PWM1 and 2, 3 and 4, 5 and 6. Otherwise, if you turn on 1 and 2 at the same time, we short the DC bus and cause catastrophic fault. So that's why we need to apply deadband in between the PWM1 and PWM2. I mean the switches on the same phase, on the same leg. We need to sense the current in order to control the torque. So there are a few different ways to sense the current. We can use like isolated current sensors, which is good for high performance applications, but very expensive. Like a single current sensor, isolated sensor, is like around $20, $25 today. So instead, what we do, we use shunt resistors at the bottom of the legs, low side, shunt resistors as shown on the slide. So we measure the voltage across these shunt resistors. Since these are connected low side, okay, we observe voltage pulses when we turn on PWM2 and PWM4. So the voltage across these resistors are, combination of composed of pulses, very narrow notches. So that's why ADC should be very fast to sense the voltage level, which means a current level indirectly, within that limited time period. Because pulses, they are very narrow. And all our C2000 devices can easily, sense the current. And when you look at the graph window while spinning the motor, you don't see those pulses. What you see is nice pure sine waveform without any kind of noise. And typically C2000 controllers, very fast, and they convert the signal in between 80 nanosecond to 250 nanosecond typically. And if you apply, like if you control the motor with sensor, if you do sensor control, then we use incremental encoders, and the pulses of incremental encoder goes to QVP circuit, which is on-chip circuit, and convert the pulses to position information, and then in the code we convert it to speed information as well. For PMSM type of motors, we need to know where the rotor is exactly. We need to know the exact rotor position information. That's very important. In addition to this scheme, we have like sensorless operation as well. Here in this slide, I'm going to talk about a sensor BLDC motor trapezoidal control. Again, we use three-phase inverter, 6 PWMs. And since this is sensor control, the customer needs to connect a Hall sensor. Most BLDC motors come with the Hall sensors. So the pulse goes to capture unit or GPIOs in order to sense the rotor position, magnet positions. So in each 360-degree angle, we get like 6 pulses through the Hall sensors and convert this to position information. As you see here, we sense the low side DC current in order to control the torque. And what else we have? PWMs, communication, serial communication, and parallel communication. Yeah, that's pretty much what it is. This is of course very high level block diagram. And here we have sensorless trapezoidal control. What we do, we don't use Hall effect sensors. Instead, we sense the back EMF of the BLDC motor. That's why we have voltage dividers, simple resistors, nothing else, voltage dividers. And we sense the back EMFs using ADC channels of the controller. What we do, we basically sense the zero crossings of the back EMF waveforms. That's how we determine the position of the rotor and then make a decision about the commutation sector. And again, we can use DC shunt in order to sense the current and control the torque. That's an option we might not use as well, because when we close the speed loop, the torque is indirectly controlled. The other type of motor is induction motor. Induction motors are, highly reliable, low cost, and they are very robust indeed. Like, we don't have brush, we don't have magnets, we have nothing, just the cage as shown here on the slide. So what people do, first of all, they manufacture the rotor with the rotor slots on it, and then they melt the aluminum or copper in those slots, and that's how they create the cage. And when we excite the power the stator, the rotating field indirectly creates flux on the rotor, on the cage bars. So that's how we create an indirect electromagnet on the induction rotor, and that induced field vector follows the stator field vector. The basic difference between induction motor and the other PM type of motors are, induction motor is not synchronous, which is okay. When your stator field spin at like 1500 RPM, the rotor will be spinning like around 1400 RPM, depending on the load. The disadvantage of the induction motor is the control of induction motor is not straightforward. It's quite complicated. Again, we need mathematically intensive algorithms to control. Using induction control, it's very hard to control the position, almost impossible. Instead, we control speed and torque. For speed and torque applications, speed control and torque control applications, induction motor is a very robust and cheap and good candidate. Of course, the power density is not as high as PM motors because we need to create the flux by ourselves. On the other hand, in PM motors, the flux is created by the magnets. Here, induction motor we are creating, so that's why we need to inject more power to create the flux. That's why the power density is less when compared to PMSM type of motors, and that's why people prefer PM type of motors for like electrical vehicles or hybrid electric vehicles or high-end applications, where the volume is important. Physical volume is important. So we can control the induction motor using V by F, scalar control or vector control. And the driver is again three-phase inverter. And here is the diagram. This is pretty much similar to PM motors. 6 PWMs, three-phase inverter, and the currents are sensed through the shunt resistors. And you can implement either censored or sensorless. Commonly QEP, incremental encoder or tachometers are used for induction motors. Since we don't need very precise position information for induction motor, people prefer like cheap tachometers, which are fine, because we don't need to know the precise position, but we need to know the speed. So that's why like 10 pulse per revolution type of encoders, or tachometers are good enough for induction motors. But on the other hand, for PMSM type of motors, people go like above 1000 PPR, pulse per revolution. And typically I use 2000 pulse per revolution for precise control. And currents are sensed through the shunt resistors in our applications. And again, we can use the capture or QEP circuit. Capture is used for tachometers. QEP circuit, on-chip QEP circuit is used for incremental encoders. Incremental encoders, basically they provide like 2 pulses with 90-degree phase shift, AB pulses, and there is an index, which is just single pulse per revolution, and reset the counter. So A and B pulses, help us to calculate the position, and index pulse reset the counter each time. Again, incremental encoders are used for precise applications, and capture pins are used for low-cost applications, especially for induction motor. Like very low count encoders or tachometers are good enough, and the capture can easily calculate the time in between 2 pulses and convert it to speed. Here I'm going to talk about three-phase operation. Now, as you know, in three-phase motors, PMSM type of motor, BLDC type of motor, induction type of motors, the stator has 3 phases and several slots, and the phase windings are distributed through the stator structure. Here, the windings, in this slide, the windings are not distributed. Instead, phase A, phase B, and phase C are shown as a single coil or turn, which is not indeed. We distribute all these windings to create sinusoidal back EMF or field vector. So as you see here, we have like 3 black arrows which represent the field vectors created by each windings. FA is created by phase A. Again, if you remember from right-hand rule, physics, high school physics, according to the right-hand rule, the black FA vector is created by phase A windings, and FB is created by phase C windings, and FC is created by phase C windings. And if you add these 3 vectors up, the resultant vector will be the pink vector. Okay, and this vector will be rotating in the air gap, counterclockwise or clockwise depending on the motor direction. And when we control the motor, basically what we do, we are controlling the amplitude and frequency of this pink vector. That's pretty much it. I mean, if I want to summarize the motor control in just a single sentence, especially in field control, we are controlling the frequency and amplitude of this vector. Now, in the next slide, we are going to, there is a nice animation. We are going to see how we create this resultant vector in the air gap. Okay, can you see it? Okay. Now, when you look at the phase A, phase B, and phase C windings, since these are sinusoidal waveforms, the amplitude of these phase voltages and currents are increasing and decreasing, going to the negative side. And when we add these three vectors simultaneously, the resultant vector will be the black one, which is the field vector, stator field vector, and it's rotating. That's what we call rotating field vector. And mostly what happens when we control the motor, the rotor magnets or the flux or the field vector we create on the rotor follows this rotating field vector. That's how motor spins. Now we have another animation. Here we are going to see exact same thing in the time domain. Okay, again, blue, green, and red waveforms belongs to phases, and the black one is the resultant vector, which is a traveling or rotating field vector in the stator or in the air gap. So basically what we are doing, we are controlling the amplitude and frequency of the black waveform. And in the next slide, I'm going to show both of them together so that you can, compare the previous two slides. Okay, yeah. Here I combined both of them. So on the left-hand side, we have the vectorial representation of the current, phase A current or voltage quantities, and on the right-hand side, we observe the sinusoidal distribution. So when we say like three-phase operation, basically, we mean this like three-phase phase currents and vectors and resultant vector and control these simultaneously. Okay, now the next type of motor is a switch reluctance motor. I'm not going to talk about this in detail, but I just want to give a little bit information about this. The switch reluctance motor are, I think these are the most robust motors because we don't have magnets, we don't have brushes. It's nothing but just chunk of metal. We have windings on the stator side, and we have a few stator poles and rotor poles. What we do, we excite the stator windings, only one pole, opposite poles each time, and the rotor poles are attracted by the stator poles, which are excited at that time, of course. And the basic philosophy is minimizing the reluctance, or if I say in other words, like when we excite the coil, the stator pole becomes sort of electromagnet, and the rotor is, of course, metal, and that's why the metal is attracted by the electromagnet on the stator side. That's how switch reluctance motors spin. These are relatively cheap, very robust. I won't say it's like high power density because we need to again create our own flux. There are like various geometries as you see in the slide, but the problem of this type of motors, they create too much acoustic noise and torque ripples because the force distribution in the air gap is not uniform. Instead, we are exciting the opposite poles at the same time. So that's why the physical force across the stator poles are non-uniform. In three-phase motors, the force is distributed, around the stator, but here only the opposite poles are excited. So that's why non-uniform force cause acoustic noise and torque ripple. So that's why for high-end applications, these type of motors are not very popular. And the next type of motor is step motors. I'm sure you all know about step motors. There are like three type of motors: reluctance, variable reluctance step motors, PM motors, step motors, and the hybrid motors. Hybrid motors are the new topology, and this is very popular, and that's excellent for position control. You can go up to 400 steps per revolution. So if you need like very precise position control, hybrid step motors are perfect candidates for these kind of applications. Okay, now I'm going to talk about the motor control. So far we talked about the motor types. In the motor control, we basically aim like maximum efficiency, good transients, maximum torque generation. On the other hand, low VMI, low acoustic noise, and we want a minimum, reactive power. Maximum power factor correction, and board cost. Driver cost and development time is also another factor when we choose the motor or when we think about the motor control. The first type of motor control I'm going to talk today is a scalar control. This is basically applied for only induction motor today, and this is very popular actually. Today, again, like 70-80% of the induction motors are driven by scalar control. This is not very efficient way to control induction motor, and the transients are poor, as you see on the right hand side, the bottom picture. The transients, we see a lot of oscillation. It's because we don't have full control over the torque and flux components. And we call it V by F because we try to keep voltage divided by frequency ratio, V by F ratio constant. This helps us keep the flux phi m component constant. Again, here we are imitating DC motor. In DC motor, as I mentioned earlier, the field flux is kept constant, and we control only the torque component. Here we keep the flux constant, but the torque component is not controlled. Instead, it's dependent on the amount of the load. So since we cannot control the torque component, but control only flux component, the transient performance of scalar control is poor when compared to vector control or FOC. But the good thing about the V by F is, it's easy to implement, and we don't need position information, we don't need feedback. And the problem is when you go to higher speeds or lower speeds, especially lower speed, if you look at the graph on the left-hand side, it's almost impossible to keep the ratio constant because at low voltages, the voltage drop across the motor parameters like RS and LS become remarkable. So we cannot neglect the voltage drop across these components anymore. So that's why we need to compensate. So that's why we experimentally create a new profile to compensate the voltage drop across the motor impedance. RS and LS, stator impedances. And torque delivery, again, it's not optimized. This is not the most efficient way to control the induction motor, but simple and cheap. This is the block diagram of the V by F control. Here the loop is closed with the speed feedback. I mean, VYF can be implemented open loop, that's okay. But if you want like high precision speed control, in this case you need to close the loop using the speed feedback. So here the speed feedback and the reference are compared, and the error is fed to PID block, and the PID controls the voltage and the frequency. This V/F block is nothing but a lookup table. So PID makes the decision depending on the error, amount of error. PID picks one of the value here, and then the reference voltage values are sent to space vector PWM, and the PWM circuit creates the PWM waveforms. Now I'm going to talk about the vector control. In vector control, we separately control the field and torque. Here I put the DC motor purposely, DC motor model purposely, because it's pretty much like DC motor. Field and armature are separately controlled in DC motor, and and we keep the field constant during the whole operation. In the vector control, we are going to do the same thing. We will control field and armature independently and keep the flux component constant. Again, we'll try to keep the, as I mentioned earlier, the blue stator vector and the red rotor vector orthogonal to each other to maximize the torque production. And the benefit of vector control, the torque ripples are minimum, and the dynamic performance is almost perfect because we control both the torque generation and the flux generation independently. And of course we need rotor position. That's the disadvantage of FOC. And low speed is not a big deal for FOC. We can go down to like 0 speed using FOC, as long as we have a good speed or position feedback. So here's the block diagram of field orient control. Basically what we do, we sense the phase currents. Okay, we phase the phase A and phase B currents as shown here. I mean, 2-phase current information is enough. We can create the third one in the code because all 3 phases add up to 0 mathematically. And we sense the phase A and phase B currents. And then after like 2 alpha, beta, and DQ transformation, we call these Park and Clark transformation, we decouple the current into 2 components, ID and IQ components. ID represent the flux and IQ represent the torque. So we have chance to control flux and torque independently. Okay, and we compare these flux and torque feedback with the flux and torque references. Now I'm focusing on the orange region. So we compare the ID and IQ feedback, torque and flux feedback, with the references, and the error is fed to PIDs. And the reference voltages from the PID output are again converted to like 3-phase voltages, and then the PWM waveforms are generated. Now here I want to talk about these transformations, the blue, alpha, beta, and DQ blocks. These are called Park and Clark, and what they do, they convert the 3-phase to 2-phase alpha, beta first, and then they decouple the torque and flux components. So these are very useful to transformation for 3-phase motor control. So we convert from 3-phase to 2-phase, and then we decouple the torque and flux components. And we separately control the torque and flux. And after regulating the errors, again, what we do, we convert from 2-phase to 3-phase. Okay, the DQ block, upper DQ block is the inverse Park and inverse Clark transformation. From 2-phase, we convert from 2-phase to 3-phase. The good thing about this transformation is ID and IQ components are DC. So controlling the DC quantities are pretty simple. So it makes the life very easy. Again, what we do, we sense the 3-phase current, convert it to 2-phase AC, and then convert it to two-phase DC, which automatically decouples torque and flux components. Now, if you want to control the speed, of course, you need to close the speed loop as well, and then feed the error to speed PID, and the speed PID will indirectly control the torque here. Because if you need to increase the speed, you need more torque. Okay, so the speed PID output becomes sort of torque reference. Here is FOC control. Okay, here is FOC control of PM motor. Here I eliminated the sensor. If you want to, we can close the speed loop without the sensor. What we do instead, using current information and voltage information, we can estimate the position and indirectly create the, estimate the speed, and then control both the position and speed by means of this position estimator. In our applications, we mostly use sliding mode observer for PM type of motors. So sensorless control, in sensorless control, instead of using an encoder, we use a mathematically intensive algorithm which uses current and voltage informations, calculates flux and back EMF, and then estimate the position of the rotor. And we feed this position information to transformation matrices. And again, we estimate the speed using this position information. Now, if you look at the right-hand side, I put the number of cycles of each block. So typically, a sensorless FOC, which is one of the most challenging mathematically intensive one, for piccolo kind of devices like 60 megahertz, a 60 megahertz sensorless FOC use like less than 20% of the CPU. This number, it's great. I think when I compare this number with our competitors, I think we are the best in terms of CPU utilization. So we use only 20% of CPU. I'm talking about like Piccolo A and Piccolo B devices, 60 megahertz devices, which means that we can control like up to 4 motors, sensorless PM motors, instantaneously. And what we did, we controlled like 2 motor plus PFC. PFC is at 100 kilohertz, and motors are the switching frequency of motors are 10K, and the PFC is 100K. And 2 motor plus PFC is using like 65% of CPU. Again, we have like 35% room for the customer for background and slow tests, protection, system monitoring, keyboarding, and some other functions. Here I want to visually show the transformation, park and clock transformation. If you look at the left-hand side, this is like typical three-phase current waveforms, and these are the space vectors, as I mentioned earlier, and blue vector is the rotating vector, resultant vector. Now here we have 3 axes. Okay. Now the philosophy is we can represent the blue vector not with the 3-phase but 2-phase, which is possible, right? Alpha and beta axes. So the transformation matrix, what it does, it converts the 3-phase quantity to 2-phase quantity. So the projections on the beta and alpha are shown below. 2-phase AC, which are orthogonal to each other. 90 degree phase shift. We have 90 degree phase shift in between alpha and beta components. So what we did, we represented the same vector with 2 axes. That's what we call clock transformation. And the park transformation, we start spinning the axis as well. Not only the vector. Vector is spinning, and we start spinning the axis synchronously with the vector itself. So that's why the projections of the blue vector, the field vector, or the current vector, is constant and DC, because the axis and the vector are stationary with respect to each other. So here, as you see, we decouple the flux and torque components and convert them to DC, and we easily control these DC quantities. this is the basic philosophy of FOC, independent control of torque and flux. And these are the very popular transformations: Clark and Park. Clark convert to two-phase AC, Park convert to two-phase DC, and decouple the flux and torque components. Okay, here is the summary of the overall picture. Now as a TI, what we have like block diagrams. Okay, this is almost identical to control block diagram I showed earlier. Now we have the block diagram, and the blocks here are software modules, which are like C functions. Okay, so inputs and outputs of these C functions are very well defined, and you can connect them, link them to each other in the code. Okay, like for example, run the Clark first, and then link the output of Clark to inputs of Park, and then call the Park function, and then link the output of Park to PID inputs, and then call the PID function, kind of, So we have very well defined block diagrams, software modules, libraries, application notes, and we have almost everything that we need for motor control, PID regulators, Park Clark transformation ramp generators. We have almost like 30 different, very basic DMC motor control, digital motor control software modules ready to use. And we get very positive feedback from the customers. And we have, like, when you download the projects come with the PDFs, which are the explanations of each and every library module. You can get more information about the cycles, about the mathematical background of the function. If you don't understand the code directly, you can check the mathematical background and see how the function works. Again, these are very helpful documents for user-friendly applications, and we get a lot of positive feedback about all these. And of course, we use IQMath, which is a virtual floating point. Although most of the controllers we have are fixed point, by means of thanks to IQMath, we can develop the code like floating point. We have some special IQMath functions. And in addition to floating point feature, IQMath has a lot of trigonometric function as well, so you don't need to worry about sine and cosine, arctangent. There are like several functions ready to use. Here are the application notes and projects we have. Sorry, these are projects. So when you download each and every project, it comes with the application notes, user manual, library modules, and everything. We have several ACI, sensor, sensorless, V/F, FOC application, BLDC projects, PMSM projects, switch reluctance projects, DC motor, SEP motor. So when you go to motor control software library, you'll see all these applications. I want to skip the PWM part. I had a few slides about the space vector generation. Okay, let me quickly go through this. What we do in order to create a waveform, okay, since our platform is digital, okay, we only have chance to create pulses, and we can control the duty cycle of the pulses. That's the only possibility we have. So what we do, we control the duty cycle of the pulses, and the motor itself is sort of like behaves like a low pass filter. And although the combination of pulses looks meaningless, the low pass filtered when we low pass filter the pulses, we will see the fundamental component like the blue vector here, the sinusoidal vector, which is a voltage waveform and low pass filter form of the pulses. Now there are a few different types of PWM generation. Now this is the traditional way. What we do here, we compare a high frequency triangular waveform. This is like very fast, like 10K triangular waveform with the like 60-50 Hertz or less stator voltage, and the intersection of these two waveforms determines the pulse width. So that's how we create the PWM pulses. This is a traditional and simple way. And yeah, I mean, people don't need to have like powerful controllers in order to implement this. And still, some of our competitors are using this algorithm. And there's another one, I mean, more advanced, mathematically intensive, and more efficient way to do this, space vector. In space vector, we have like 6 key vectors, sector vectors, okay? And these 1, 0, 0, 0, 1, 1 type of, numbers, these represent the switch state, like 1, 0, 0 means the upper switch of A is on, upper switch of B is off, upper switch of C is off, okay? And if you look at the V60, upper switch of A is off, B is on, C is on. Okay, so these are the vectors, and the blue one is the vector that we want to control, field vector, okay, or voltage vector. So what we do, we calculate the projections of the blue vector on like V0 and V60, and these projections are the duty cycles of the PWM at instantaneous duty cycles of the PWM pulses. So of course this blue vector keeps spinning and the projections on the vectors change. So that's why we update the duty cycle of the PWM continuously, like at 10K or 20K depending on the ISR. And we have like 6 sectors, and this vector goes to the next sector, S2, S3, S4, and in that case we use the neighboring vectors to calculate the duty cycles. I mean, the good thing about this is the low-pass filtered duty cycle waveform. It looks like sine, but not exactly sine. It's because we inject third harmonic, okay, indirectly. So what we do, we taper, we cut the top of the sine. If you look at the Fourier expansion, we still have the fundamental component that we need to spin the motor. The good thing about this waveform is the third harmonic does not have a path on the Y-connected or delta-connected motors, so it doesn't hurt the system. So what we are doing, we are like saturating or tapering the peak of the sine. So this helps us to like control the motor more efficiently because we need less DC bus voltage in order to create the same sine wave, because the peak value is tapered, okay, of the sine is tapered. So that's why with less DC bus voltage we can create the same sine waveform. So we can use like low rated caps, which are the most expensive components of the drive, and reduce the switching losses because we reduce the DC bus voltage. And again, the DC bus voltage control, basically creates the EMI because of the stress. And again, we reduce the EMI as well. This is, of course, mathematically intensive, so all C2000 controllers use this algorithm. I want to skip these slides. So I guess today a few people from our team will going to talk about all these tools. So that's why I want to skip them. I don't have enough time to talk about these. I'm going to talk about dual axis motor we recently released. 2 motor plus PFC board. So what we did, we prepared a platform both for Piccolo A and Piccolo B, and this is a motor control platform that people can experiment, like single motor control, PFC plus single motor control. We have front edge PFC stage which controls the power factor and boost the DC bus voltage and control the DC bus voltage and keep it stabilized. And the next slide shows the capability, the maximum capability, 2 motors plus PFC. again, as I mentioned earlier, both the 60 megahertz Piccolo devices use like 65% of the CPU in order to implement 2 motors plus PFC. As you see here on the picture, it might be a little bit confusing. We have like 4 legs, but for 3-phase motor we need 3 legs. It's because the DRV chips, the drive chips we use, these are TI drives, DRV chips. They have like 4 legs. That's why we showed all of them, but we don't use the 4th one. We use the first 3 legs. And again, we sense the current through the shunt resistors. We spin the motors at 10K, and we run the PFC at 100K. Here is the picture of the dual axis board. Now the blue ones are the first and second motor drive stages, and the IPMs are under the heatsink. And we have onboard emulator, so the customer can directly connect the board to USB without JTAG. And the red part is the connector 100 DIMM for control cards. So far I used like 2808 Piccolo A and Piccolo B with this card, so the customer can evaluate any controller he wants to use. And the yellow part is the PFC stage. Yeah, so using this board, the customer can experiment single motor control, PFC only, 1 motor plus PFC, 2 motors plus PFC. So right now we have all these combinations. As far as I know, the 2 motor plus PFC project is not released. It's not on the web page, but if you contact us, we can provide the code to you. But the other ones, motor only, PFC only, and 1 motor plus PFC are already released, and they're on the web page right now. And I want to talk about the incremental builds. And I'll skip these slides. I think these slides are available. You can check them, and if you have any question, you can ask your questions, email your questions. We can answer in time. So these are the modules used for PFC. Again, I'm going to skip this. Okay. Now I'm going to talk about the incremental level within the next 3 minutes and finish the presentation. What we do, we ask the customer gradually develop their code. Actually, the code is ready, for the customer to use. And what we do, we divide the code. We prepare the code in like 5-6 different incremental builds. The first one, for example, as you see on the slide, we ask the customer disconnect the motor, and run the code and observe the necessary waveforms like duty cycles of the space vector, both from inverter output and from the graph window. And we want the customer, make sure that the code is working okay. The initializations are done correctly. So as a startup, everything is okay, and we are ready to go to the next phase. So in the next phase, we ask the customer. This is valid for all kind of like motor control applications we have on the website. We all implement them, phase by phase. So on the second phase, we ask the customer connect the motor and spin the motor open loop, and check the current waveforms, compensate the offset if there is an offset on the current waveforms, and again check the duty cycles and make sure that the motor is spinning. And there are some disconnected modules, as you see here. We ask the customer check the outputs of these modules and see whether they are operating correctly or not before closing the loops. And on the third stage, we close the torque loop or current loop. We control ID and IQ components, flux and torque components, independently, but we don't do speed control here. Again, so we have a few questions to customer on the user manual. These are all explained in the user manual PDFs in detail. And we indicate the customers the critical points and checkpoints. We have a checklist there. And here we closed only the current or torque loop. And in the next slide, we ask the customer add the sensorless algorithms, but do not close the sensorless speed loop. Just connect them and put them in the code and watch the outputs from watch window and graph window and make sure that they are working good. And then at the last phase, we ask the customer close the speed loop using the sensorless algorithms and speed PID. And at this point, the customer should be done, pretty much done. And after that, we ask the customer to tune his system or her system under different speed and load conditions. And for dual axis project, as a next phase, since the motors are identical, we ask the customer to connect both motors and spin them simultaneously. Yeah, I think that's pretty much it for today. Thank you for all and for joining this presentation.